Let's have a look at orbits, their inclination, and why we can't just go to the ISS at any point in time on any day, and why we have to actually wait for a specific date and time to match up orbits with the ISS. So what you're seeing on screen right now is the most efficient type of orbits. It's the so-called equatorial orbit, where you launch right on the equator and you stay there. So in this case, we're launching eastwards, which is most efficient since the Earth also rotates eastwards, and it can give us a little boost of just a few hundred meters per second, but that is very efficient already. You see, this rocket is not very realistic. It's going into orbit very quickly, so quickly, in fact, that the atmosphere is heating it up, and you see those effects on there. You normally only get those on re-entering the atmosphere when you're already going very quickly. So you can see right now we're on a suborbital trajectory. That's basically how it looks when you throw something really, really fast. But this way we're just falling back to Earth. So we want to get faster. So how we're doing this is just, well, accelerating in our current direction even more. So let's have a look at this. The first stage of this rocket is now falling back to Earth. Of course, SpaceX would land this booster, but this is, of course, beyond the scope of this video. So we're just planning out our future orbit and then starting the burn. And now we can see that our trajectory is widening out, and now it's actually an orbit. And as we can see now, the orbit is exactly in the plane of rotation of this planet. And we're actually going faster than the planet is rotating. Okay, so this is the second type of orbit. We're just taking an inclination of 42, maybe 45 degrees. That's somewhat similar to the space station. So we're not going directly eastwards. We're losing a bit of efficiency there, but this gives us some advantages that we can see in just a few seconds. This rocket is even faster. It's quite ridiculous. This is almost what maybe a nuclear missile would look like, going into space very, very quickly with a lot of thrust. And now we can see the same thing again, a suborbital trajectory first, and now speeding up a bit more and expanding that into a full orbit. The altitude of this orbit will be more or less the same, so just above 80 kilometers, which in this game is working fine, but 80 kilometers is still way too low for an orbit around Earth. Just for comparison, the ISS, for example, is orbiting at around 400 kilometers altitude. Now we can see that the planet is rotating below this orbit. And now, as we look there on the map, the little dot at what looks like Africa is a launch center. And only when this lines up, then we can launch a new rocket. So let's try launch another rocket and dock it. So we could imagine that this is the Crew Dragon capsule on a Falcon 9 rocket that is launching tonight with SpaceX. So the rocket that is already in orbit there in this inclined orbit could be the ISS, and we're trying to dock with it. So in this case, this is sort of on a half orbit. So we're now launching northwards, while before it was eastwards. But that's just essentially meeting on the other half of the orbit. So the orbit stays stationary while the Earth rotates below it. That's of course because the Earth is just, well, one gravitational point if you, in this very simple simulation, and you're no longer rotating with it because there's no atmosphere, there's no surface to keep you rotating. So that's essentially how this goes. So now we've brought this third rocket into orbit. We now see that the sort of ISS model is lagging a bit behind. So what we can do in this case is to expand our orbit a bit, because orbital mechanics works in such a way that orbits that are larger out will be a bit slower. So you take more time to complete one rotation. And you're also, that's not just because the orbit is larger, but you're also going slower. That's similar in principle to how an ice skater can bring their arms closer and then rotate much faster. So we're going to match up orbits by this and then see that we drift closer together. What you see now with this inclined orbit is that as Earth rotates at one speed and we orbit at a much faster speed, we're going eventually over almost every path on Earth, in this case, except for the very northern and southern poles. So if you have places like the like in Kazakhstan, where Soyuz launches from, which are a lot higher inclinated, then you can only do these kinds of orbits because an equatorial orbit just would never pass above those. This is the reason why the ISS is in an inclinated orbit. This was because the ISS was initially intended, and it still is, a collaboration between US and Russia. So Russians would not have been able to launch in this case if the ISS wasn't inclinated that much. So now we're just trying to kill the relative velocity with the other spacecraft, and that eventually gets us close. So we can look in the orbit, we can look at the other spacecraft, and we see that now we have the exact same orbit and the Earth is just passing below us.